to make a graph at nothing.
You were ready.
I'll tell you that.
Okay, you were ready.
Yeah. You got any? Agaroma. Fancy chalk.
You want one?
Thank you. What gentleman?
Okay, so I think we can start. So it's my pleasure to welcome Mark Powell, who will give a series of lectures on symmetries of four manifolds, and now we start with the
Thank you very much for the invitation. It's great to be here. Yeah, so I want to try and tell you about symmetries of four manifolds, and in particular, focusing in particular on mapping class groups of four manifolds, because those are the ones that we know the best about. So in general, we know the most about. So X is going to be a closed simply connected topological four manifold. So that's just kind of standing notation for, if I don't say what X is, then it's one of those. Although it may vary in time, but just so I've got that fixed. So I want to think about, actually this is something we could think about more generally for four manifolds or any dimensional manifolds. I want to think about the topological group of homeomorphisms of X to itself. So this is a topological group of homeomorphisms. And the plus here denotes that they are. So I could do this without the plus and just think about all homeomorphisms, or I could require that they're orientation preserving. So obviously that only makes sense if X is orientable. In the case of simply connected manifolds, it's going to be orientable automatically, but in general, of course it might not be, but if it is, then we can put this plus here and consider the orientation preserving ones. So orientation preserving is always, from now on, just going to be called OP, because I don't like writing orientation preserving. So this is a group, just because we have composition. So that's easy. I mean, we can compose homeomorphisms, they have inverses, and the topology, well, so then we use what's called this won't really show up very much, but we use what's called the compact open topology. So you can read all about it in the appendix of Hatcher, if you didn't already. And this makes this into a topological group. So this is a nice object to study. And I would say one of the key goals of at least a certain type of person who likes to study manifolds would be to understand maybe this group, or maybe more accurately, what we really want to understand is the homotopy type of this group. What are its homotopy groups? What are its homology groups? If you understand the homotopy classes of maps from Sn minus 1 to homeo of X, then you understand vector bundles of the form of this form, or sorry, not vector bundles, sorry, fiber bundles with fiber X. So if I think about homotopy classes of maps like this, correspond to fiber bundles up to isomorphism of fiber bundles. Because if I take I always have a trivial fiber bundle on the n disk, and I have another trivial one on the n disk, and then this such a map from S. So this is supposed to be dn and dn, and this is Sn minus 1. Then the way that we glue the bundle together, so that here I take dn cross x, and here I take dn cross x, and then we glue it together using such a map, and we get a bundle of this form. And so this is just the basic example of why we might care about the homotopy groups of this thing. Is even if you don't agree that, I mean, for one thing, I think just studying symmetries of manifolds is cool, but even if you only wanted to classify manifolds, one of the great classes of manifolds we might like to understand is fiber bundles. You take a base and a fiber and you get a new manifold, and the way we would like to do that would be to understand these spaces. So this is just supposed to be some motivation that these are cool things to consider. So in particular, I want to think about pi 0 of this thing. So pi 0 homeo of x and pi 0 homeo plus of x. So this is the mapping class group. Of x and the orientation preserving mapping class group of x. I put the plus there. And yeah, I mean, well, I would like to understand the whole homotopy type, but it's quite difficult. So one of the things we actually can understand is this thing. And of course, in general, maybe some of you are saying, well, I'd really like to also think about the same thing, but with diff instead of hom here, and those are also very interesting, and I will kind of talk about the smooth mapping class groups as well. But I want to focus on the topological version because these are the ones that we can actually compute and figure out the answer for. I really like I like it when we can completely know the answer, and it's in the topological category that we can actually do that. But it's certainly very interesting to compare with the smooth category and try and figure out as much as we can about that as well. Well, what is the answer? So the theorem, which is quite old, it's due to Craig and Perron and Quinn, I would say, and it says that this, well, so I'm going to think about the orientation preserving one, and given a homeomorphism, what I can do is I can take the induced map on second homology. So this is again now x is this. We're now completely restricting to x4 is closed and one connected again. So I'm going to write one connected instead of simply connected because it's quicker and it means the same thing. And so what I can do is I can take the induced map on second homology. So that's now an isomorphism of the second homology group. But it has an extra property, which is that it preserves the intersection form. So I'll say what this is in a second. So if we then think of automorphisms of the second homology with together which preserve the intersection form, then there's a map from here to here given by taking the induced map on second homology. This thing is actually an isomorphism. So this is a very nice clean statement, and yeah, so one of my goals is to explain the proof of this theorem. So I think many people know the statement, but I think not too many people know the proof. And the reason, well, I mean, so this is sort of done in the 80s. So in a sense, why am I telling you about a theorem from 40 years ago? For one thing, I think it's good to understand the proofs of things if we're going to use them a lot. But also because, okay, this is in a very special situation of closed, simply connected manifolds. And I think there's a lot more to be done in extending this in all sorts of different ways. So I think if you understand the proofs, then you can... I want to just explain the proof in the simplest possible case, so that because that's the easiest way to understand the ideas, but then I sort of hope that it will motivate at least some people to just think about it further, because I think there's an awful lot to be done, a lot more that we should know about mapping class groups of four manifolds and in general the homotopy type of them. Maybe just to make sure I've actually explained the statement completely. So for such a four manifold, H2 of X is always a free abelian group for some M. So there's no, it's finally generated, and there's no torsion, because if it had torsion, that would appear in H upper 3, which would then appear in H lower 1 by universal coefficients and Poincare duality. So, but then there's no H lower 1 because it's simply connected. So it's always free, and lambda x denotes the intersection form. So I said that in words, but so this is the intersection pairing. So what I do, I take two classes and the quickest way of writing it down is I take the Poincare duality inverse of y, so that gives me an element in H upper 2 of x, and then I pair it with x. This is the Kronecker pairing, and then I get an integer. You could also say, you might have seen people say, take the Poincare duality inverse of both of them, take the cut product together, and then evaluate on the fundamental class. You could also define it like that. It's the same. It's just a quicker way of writing it. And one that generalizes more easily to non-simply connected manifolds, which I like. Okay, anything else I wanted to say about it? Oh yeah, so what does it mean to be... So I've already stated the... So this is, we say this is an automorphism of lambda x if just if it preserves the intersection form in the obvious way. Hopefully that's obvious. So that's what this group is about on the right. Okay, so any questions so far? Also, is the writing legible, big enough? Okay. You're in the front, so it's for you. Yeah, so is the statement and the aims, well, I'm going to write down more aims in a minute, but so far so good. Yeah, maybe I should say, so we're talking about four manifolds here. I like four manifolds. I think, so, mapping class groups of surfaces, that's a whole subject. In a sense, we understand them quite well, but there's definitely things about those groups that are still to be understood. So that's very interesting, but very different methods from what one uses for other manifolds. Mapping class groups of three manifolds are extremely well understood. There's a lot of excellent theorems on that. Yeah, well, if you go to my website, I made a page recently which contains many links and notes on all the things we know about those groups. So I think it's a very interesting topic, but it is something that we know pretty well. Like if someone gives you a 3-manifold and asks you to figure out the fundamental group, it's not going to be, figure out the mapping class group, it's not going to be easy because you're going to have to read a lot of papers, but somehow in the literature the answer will be there somewhere. I think it's, whereas now in high dimensions, I mean what we're going to do in the topological category in 4 manifolds is going to be somehow motivated by the way that one computes mapping class groups for high dimensional manifolds, or at least tries to compute it. It's not to say that for high dimensional manifolds you can just, well, high dimensional means dimension at least 5, you can just compute the things. But there is a theory and there's a program that one can try and follow. And so, for example, there are many cases where it's known. So, for example, for S manifolds of the form Sn cross Sn, we have a very good understanding of the mapping class groups. So the things that are highly connected, it's easier. So there's certainly lots to be done, but there is a theory. And in 4D, the theory is only partially developed. So that's sort of why dimension 4. As usual, the answer is, well, because we don't know as much in 4D as we do about the other ones. So that's maybe not a surprise if you've heard anyone try and motivate talking about 4 dimensions before, but it is correct, I claim. Okay, so what are the aims? So one is, explain the proof. And the key concept is to talk about the concept of pseudoisotopy. So I need to introduce pseudoisotopy and explain how that lets us break the proof up into 2 steps. Other things I'd like to do is generalize to think about when the boundary is not empty. And I'd definitely like to, as much as possible, compare with the smooth category. So we can talk about exotic diffeomorphisms, meaning diffeomorphisms that are topologically but not smoothly isotopic. We can talk about non-smoothable homomorphisms, so homomorphisms that exist but are not isotopic to any diffeomorphism. We want to talk about corks, and and then the other thing that I'll try and mention is applications to surfaces. So for those of you who were here last week, one of the things at the end of my talk last week was an application of mapping class groups of 4 manifolds with boundary to understanding surfaces in 4 manifolds, in particular the simple spines. It doesn't matter if that you didn't see that, but that's so that's what one of the motivations anyway for thinking about this. Okay, and then of course. I want to talk about open problems, or maybe future directions. In particular, I'm particularly interested in cases when the fundamental group is not trivial, because a lot more happens there, and maybe also higher homotopy. Because, we should think about that too. Pi 0 is nice, but there's also higher homotopy groups. Okay, so that's sort of this is just supposed to be a general discussion of what I'm planning to do in the next couple of days, and we'll see. Hopefully, I'll touch on all of those topics, some more than others. Okay, so I thought it'd be good to do some examples where we can actually compute this group or relate it to some algebra. So remember, we've got this pi 0 homeo plus of x isomorphic to the automorphisms of h2 of x and the intersection form. And it's important here that I have the plus, because if I want to, if I have an orientation preserving intersection, if it's an orientation preserving map, then it sends the intersection form to the intersection form. If it's orientation reversing, then it'll be an isometry from the intersection form to minus the intersection form. So I want to first of all just think about this thing, but I will then have a sequence. So once if we can understand this, then we can try to understand the whole thing. And here, if I take something, I can think of f star just as a map from h4 of x. See, this is so this is I think of this as an element of the automorphisms of Z. So it's not designed for left-handed people. So if I take a homomorphism, I can decide whether it's orientation preserving or reversing. In other words, what's the map on H4? And while I don't say there's a 0 here, it may be that no such thing exists. But if it does, then this would be onto. But at least this gives us a way of trying to also understand this thing. So example 1, we could take x to be the 4 sphere, and then of course the second homology is 0, and so there's no automorphisms of H2. And therefore, so now when we look at this sequence, we can say, okay, this one is 0. There is an orientation reversing homomorphism of the 4 sphere, because I can just do a reflection. So there exists a reflection, which is orientation reversing. And so this is onto, and therefore I know that pi 0 homeo of S4 is exactly Z mod 2. So that's sort of a basic example, but it's good to point out. Maybe worth noting that in the smooth category, it's still unknown whether there's any non-trivial orientation preserving diffeomorphism of S4 up to isotopy. So we still don't know that. Let's see. And I just thought about a couple of nice examples. Oh, excuse me. So I wanted to call it N. So if I take the connect sum of N copies of CP2, then H2 is Z mod N, and the intersection form is diagonal with ones down the diagonal, and all the diagonal entries being 1. Then what we can do is we can think about the possible symmetries of this thing, and it turns out that I can. Well, let's see. Is that going to be okay if I write at the very bottom? It's okay for you? Good. So it's maybe less okay for me. So it turns out that you can, one thing you can do is you can permute all the coordinates. Permute the coordinates, and that gives you an isometry. So I can map to the symmetric group, and in fact every such permutation is allowed. And then there is I can also send each generator, each basis element of here, I can send it to its negative, And because that still gives an automorphism of the form, because -1 squared is 1. So each of those gives me a z mod 2 to the n. And actually, it turns out that there's a short exact sequence like this. And this, the group is actually kind of a famous group. It's called the, one more thing, yeah, so this manifold has positive signature, and so you can't have any orientation reversing self-homomorphisms of it. So we know for this one that Z mod 2 on the top, this map is just, this is the zero map in this case, because there's no orientation reversing one. So pi 0 homeo of x is the same thing with the plus, and it's yeah. So what do we say? Well, it's this group, and it's called the. It's sometimes called the signed permutation group. So it's just the thing where the thing that I said, where you're allowed to do all possible permutations of the basis vectors, and you're allowed to multiply them by plus or minus 1. It's also sometimes called a Coxeter group of type. I believe it's called Bn. So I don't know. It's a famous group, and that's the mapping class group of this manifold. What about another example? If I take x to be the product of two two-spheres, then well, h2 of x is z squared, and lambda x is represented by the hyperbolic form, like that. And this is something that you can just try and find all possible 2x2 matrices that preserve this thing. That's just a simple calculation, and then it turns out that this, if you do this, then you get Z2 cross Z2, and it's generated by, well, minus the identity and crossing the coordinates. So this is not this, although it's the same matrix, it means a different thing. Here's the form. There's a matrix representing the pairing on H2, and this is a matrix representing a linear transformation, like a homomorphism from Z squared to Z squared. So these are both isomorphisms like that. And then, well, this thing has an orientation preserving. I can take R from S2 to S2, a reflection, and then I can take R cross id from S2 cross S2 to itself, and this is orientation reversing. And and this will do minus 1, 0, 0, 1 on h2 of x. And so I get a short exact sequence that goes 0 to Z2 cross Z2, the entire homeomorphism group to Z2 to 0. And so and it splits because I just gave you a map from the S2 cross S2 to itself that's order 2. So I send the generator of Z2 to that, and it gives me something order 2, so that's a homomorphism. So I get a splitting, and therefore this group is a semi-direct product of this group of order 4 with this group of order 2. And then, I don't know, if you're a bit if you're good at group theory, maybe you just know that automatically, but I had to do a little bit of computation to figure out exactly, just by working with all the different induced maps on H2, and eventually I figured out that this is actually in my list of, I mean, I know off by heart the classification of groups of order 8. There's not that many, and it's the dihedral group of order 8. Some people might call that D4, apologies to you, but I call it D8. So I taught finite group theory a couple of times, and I find it much easier to have the number represent the order, but yeah, sacrilege maybe. So it's cool. So I like this because we could actually figure out exactly what group it is, and it's not abelian. There's no reason for this thing to be an abelian group. But yeah, there's some sort of, for basic four manifolds, we actually know what the group is. Okay, maybe a good time for questions. Yeah, have to be questions. So, yeah, I mean, there's a general principle. There's this theorem saying that the homeomorphism, the mapping class group is automorphisms of the intersection form. I mean, that does tell you, in a sense, that reduces the problem to algebra, but there's still plenty to be done to figure out. It doesn't mean that you know everything about that group automatically. It was a non-trivial algebraic problem. And then, okay, so one more example would be if I take the E8 manifold. So let's see if I can do this. 3, not very well. 1, 2, 3, 4, 5, 6, 7, and then I believe it's like this. If I take a 4-ball and I attach 8 two-handles to the 4-ball using this link with framing 2 on all of them, hopefully that's the right link. This is supposed to be reminiscent of the E8 lattice, and I take that thing. That's a four manifold with boundary. The boundary is supposed to be Poincare homology sphere, so I'm told, and so I can. So Friedman proved that there exists a contractible four manifold. Whose boundary is the Poincare homology 3-sphere, and I glue that on to the boundary and I make a closed manifold. His intersection form is the E8 lattice, and this is a very important four manifold. And so again, this has non-zero signatures, so you're only going to look at the orientation preserving ones. So I call the manifold E8 as well, and this is either sometimes apparently called a Wild group or the Coxeter group. I mean, this is a very complicated group, what the automorphisms of this form is, but it's also one that people have studied a lot. It has lots of different connections to things of type. It's also called the thing of type E8. So this just means the automorphisms of the E8 lattice. So I mean, it's a lot bigger. So I looked up the size of it. Apparently, it is its order is 4 factorial times 6 factorial times 8 factorial. Whatever that's worth. That was cool. In general, it's going to be tricky to compute these things, but there is a paper of Wall where he gave explicit generators for the automorphisms, so it's something that we know about. Okay. I want to mention a couple of my favourite applications. So that's examples. I want to mention a couple of my favourite applications, which mostly have to do with the injectivity part. So, application. Number one. So there's something called the K3 manifold. So this is, well, one way of saying this is, it's not very enlightening, but at least it's a definition. So this is supposed to be all the points in CP3. So that's a 6 manifold, and we're going to cut out a codimension 1 complex submanifold. So it's going to be a real 4 manifold. So that's what we're after, and it's just. You just take the solutions to the most basic, almost easiest degree 4 homogeneous polynomial. This turns out to be a closed, one-connected, smooth 4 manifold. In complex geometry, this is a very rich subject. There's lots of K3 surfaces with different complex structures, but there is a canonical one as a smooth manifold. And it has some other constructions as well, but this is the quickest one. It's the generator of the smooth spin 4-dimensional Bordism group of manifolds. So for that reason, it's also important. I want to think about take X to be the connect sum of this thing with itself. So take 2 copies of the K3 surface and connect sum them together. And when you do connect sum, you remove a ball from this one, you remove a ball from this one, and you glue them together along S3. And that connected sum sphere lives inside there. So I have this. Connect sum, and then I have this S3 that they're glued together along. S3. And then I'm going to take a neighbourhood of that S3. So that's U, which is just a product neighbourhood, S3 cross 0, 1. Now when I have S3 cross 0, 1, I can make a diffeomorphism of this to itself. So let's call R theta from S3 to S3 be rotation by theta. So I'm just taking the S3, the whole S3, and I can just kind of rotate it around, just like how you can rotate. I basically think of this as living in R4, and then I apply the generator of pi1 of SO4 to S3, and that makes the S3 rotate around once, by a given angle. And then I can define some map from S3 cross 0, 1 to itself, and it's going to be the identity on both ends. So I just want to. This is like a Dane twist. So I want to do R 2 pi t applied to x, comma t. So I'm going to start at doing nothing, and then as I go along, I'm going to do one full rotation of the S3 as we go along this collar coordinate. And then I just want to extend by the identity on x minus u. And so that's going to give then a diffeomorphism of this connect sum to itself. And left it over there. All of the second homology of this manifold either lives in this part or it lives in this part. It can be completely supported away from the connected sum sphere, and so this thing doesn't do anything to the second homology. It's the identity. So I get. Let's see. I give it a name. Well, I just get some F from X to X, which is a diffeomorphism. And F star, oh wow, is the identity on H2. And I missed the Haggerona already. So that implies that so F is therefore topologically isotopic to the identity. Yeah, if it's trivial in pi 0, then there's a path of homeomorphisms from F to the identity map. In other words, there's an isotopy. But then there's a theorem by Kronheimer and Movka around about 2019 or 2020 that says that F is not smoothly isotopic to the identity. Man, it looks kind of hard to read. Is this still legible, or is this kind of tricky? I'm missing the. Here or here? Here. That's yeah. That's also. It's always the identity. I'm just measuring. One of them's. It acts as identity on H2, so it's topologically isotopic to the identity. But there is then this uses gauge theory. There is then a gauge theoretic proof that this thing is smoothly non-trivial. So yeah, I mean, as a diffeomorphism of S3 cross I relative to the boundary, this is definitely non-trivial. You can think about the set of spin structures of this thing, which are fixed on the boundary, and this acts non-trivially on the spin structures. But then once you include it into a bigger manifold, that goes away, and there's no reason to think that. There's no obvious reason that this should be non-trivial, and indeed, topologically it is trivial. But it turns out that yeah, smoothly it isn't. Maybe just as a contrast. I could mention that if X is, let's do CP2, connect some CP2. Although actually it only matters that one of them manifolds is CP2, and then I can do an analogous. So this thing, oh yeah, I should say this is called a Dane twist. It's completely analogous to the Dane twist on circles in surfaces. Here in this case, we also get we have another Dane twist, but in this case it is smoothly isotopic to the identity. So it does actually depend on the manifolds quite heavily. Time to stop. Okay, thanks. Great. So yeah, I'll stop the break. Yeah, thanks.
Okay. Are there any questions so far? Okay, so if there are no questions, let's thank Mark. And so we will meet in 15 minutes.
You actually told me at the time. Did I go at how much? I feel like I started. It's around about 45 minutes.
No,
Actually.
45 minutes.
Exactly. Yeah. Oh, great. Okay, thanks. Yeah, I mean, I guess one doesn't need to rush.
Basically, you were finishing the Dane twist.
Smoothly isotopic to the identity.
Can you do all these calculations for any closed form manifolds? Like the examples you gave?
The examples, well, it's going to get more harder. It's going to depend on the
In principle, it can be doable for